Good afternoon, class. We are looking at exam to review, chapter 3, differentiation rules. Which covers from 3.1 to 3.8. This is the second part, 3.4 to 3.5. 3.4, the chain rule. 3.5, implicit differentiation. Starting with the chain rule, section 3.4, the chain rule. How would you differentiate composite functions such as y equals square root of 10x plus 5 or f of x equals 10x squared minus 1 to the power of 50? The chain rule. If g is differentiable at x and f is differentiable at g of x, then the composite function f of g of x is differentiable at x. d dx of f of g of x is f prime of g of x times g prime of x. Or in Leibniz's notation, if y is f of u and u is g of x, dy dx is dy du dx. First, let's remind everybody of the composite function. If capital F of x represents f of g or f of g of x, composite function of f of x and g of x, then capital F prime of x is the derivative of this composite function, and that is f prime of g of x times g prime of x. That means you remember, when you have f of g, f is the shell function, the outer function, g is the inner function. So you differentiate the outer function, the shell function, over the inner function times the derivative of the inner function. Okay? So, for example, everybody is familiar with the power rule, where d dx of x to the power of n is nx to the power of n minus 1. Notice, if you think of x as the inner function in a sense, the derivative of x is 1. Now, if instead of x, I have a g of x to the power of n, what happens? So following this concept n, then g of x to the power of n minus 1. Going back to this one, what is the derivative of x? 1. So you don't write times 1. But what is the derivative of g of x? G prime of x. So you must write times g prime of x. That's the key with the chain rule. If we remember that, practically we are done. Okay? That's the key with the chain rule. So one example or set of examples that really help us understand would be as follows. If we look at these three cases, we want to see how to differentiate those. We start with sine of 2x. So the way I would tackle sine, cosine, trigonometric functions is this. I'm going to read sine and I'm going to pause. So I'm going to write y prime is cosine and I'm going to pause. So I'm looking at sine, everybody. The derivative is cosine. Every trigonometric function must have an argument. This is called the argument. So you need the argument. If the argument is x, you're done. Because it's not x, by the chain rule, you need the derivative of 2x, which is 2, and it becomes 2 cosine of 2x, because you're going to put that in front. The second one, I'm going to read sine, and I'm going to pause. What is the derivative of sine? Cosine. What is my argument? X squared. So I need the argument. If the argument is x, I'm done. If not, I need to multiply by its derivative 2x. And I put the 2x in front. For the last one, I'm going to rewrite this and you don't have to, but when I rewrite it as sine x to the second power, now I notice that I can use the extended power rule. To sine x to the power of 2 minus 1 is this part. And now I need g prime. So I need the derivative of the inside. The derivative of cosine is x. So I have 2 sine x cosine x. And some of you may remember this is sine of 2x, but that's not the point here, everybody. Okay, very straightforward. I hope you look at the 3 examples and see the similarities and differences, and why we use the chain rule and how we use it on each and every one of them. Okay. If you understood this, pretty much you're done with the concept of a chain rule. Let's start here. Anytime you have a number at top or at the bottom of a fraction bar, you really don't need to use the quotient rule. Rather, you're going to use your algebraic techniques to write this in a fashion that can be differentiated using the power rule. I'm going to bring this, first of all, this is x squared plus 3 to the power of 1/2. I'm going to bring it up, becomes to the power of negative 1/2. So we should know this. Now, I'm going to go with the extended power rule, everybody. First, this 4 is there, so just leave it. Then g of x to the power of n, something to the power of n. I hope you realize this is your g of x, this is your n. So I need the n, negative 1/2. Then I need g of x to the power of n minus 1. I need the same thing to the power of minus 1/2 minus 1, which makes it negative 3/2. And finally, by the chain rule, I need the derivative of the inside, g prime of x. The derivative of the inside is simply 2x. And I'm done with calculus. I'm going to just rewrite and finish off the job. So the product of these two is negative 2 times 2x is negative 4x. I'm going to take this down and write it with a positive exponent 3/2, meaning I take it to the denominator. Let me write that. I can write this as negative 4x. I can put the negative sign in front of a fraction bar over x squared plus 3 to the power of negative 3/2 changes to positive 3/2. And I'm going to rewrite it in this format because that was the format that was given. Minus 4x over the square root of x squared plus 3 to the power of 3. Remember, the denominator is the index. The numerator is the exponent. All right, we want to differentiate cosine of 3t to the power of 4. On purpose, I put the argument of cosine in a different color. And if you recall, whenever you want to differentiate trigonometric functions, if you don't want to make a mistake, here's how you read it. Cosine and stop. Pause. Cosine. So the outer function, the shell function, is cosine. What is the derivative of cosine? Negative sine, in this case u. So minus sine minus sine. But every sinusoidal function, every trigonometric function requires a argument. So it's same argument. So whatever this is, write it here, you must. Finally, you need, if this is t or x, you're done. Otherwise, you need the derivative of this piece by the chain rule, du dx, cosine of u minus sine u du dx. So we need du dx. This is your u. So you need 12 t cubed. Of course, this, we put it in front, and we are done. We want to differentiate this. And again, it's extremely important to know when to use the quotient rule and when not to. I hope you realize that you don't have to do that because I can simplify it as follows. This fraction x squared over x is x. This fraction 4x over x is 4. And that's it. So what is the derivative of this? 6 times x plus 4 to the power of 5. The derivative of the inside is 1. I don't have to write that. Again, don't use the quotient rule if you don't have to. I can't emphasize this enough. Now, I want to differentiate this. And I'm going to use combination of a chain rule, or if you will, even extended power rule, and the quotient rule. So if you ignore that for now, something to the power of 5, and I'm going to go with that. So 5 sits in front, y prime equals 5. Same thing, whatever it is, to the power of n minus 1. Same thing to the power of 4. Okay, everybody. Finally, I need g prime of x, which means I need the derivative of the inside, 2x plus 3 over x minus 8. So I need the derivative of this piece. And that requires the quotient rule. So if I am looking at the numerator as f, let me just write it here so because I don't want any problem. So 2x plus 3 over x minus 8. I need to differentiate this, where the top I'm going to call it f, the bottom I'm going to call it g. So f prime 2 times g, x minus 8, minus g prime 1 times f times 2x plus 3. And then just write the bottom in a parenthesis and square it. And we're done. We're just going to go with algebra to finish the job. This is the only calculus step, everybody. So to make sure everybody understands what's going on, we are going to simplify this expression. Two x minus 16 minus 2x minus 3. They add up to negative 19. Everything in the numerator simplifies to negative 19. So again, just to make sure we know what we are doing, I'm going to keep it intact just the way it is. I'm going to separate this from the top and the bottom because sometimes students don't see that this has an exponent 4 with 2 becomes 6. But I want you to see that. Okay. And so now, what is at top? 5 times negative 19 and 2x plus 3 to the power of 4. That makes it negative 95. 2x plus 3 to the power of 4. This makes it x minus 8 to the power of 4 plus 2. And that's your final answer, everybody. Again, many, many algebraic steps, not many calculus steps. All right. We want to differentiate exponential functions. We know the derivative of e to the power of x is itself. And we know the composite function says if you want to differentiate f of g of x, f prime of g of x times g prime of x. So if I want e to the power of kx, the derivative is e to the power of kx times k. This is actually this part by the chain rule. The derivative of any exponential function is itself times the derivative of the exponent by the chain rule. So this is e to the power of g of x, you can think about it. Or think about this, d dx of e to the power of g of x is itself by the chain rule times g prime of x, okay? So if I'm looking at this one, I'm gonna quickly show you how I'm gonna tackle that. I'm gonna write y prime is itself. Y, because it's an exponential. And then according to this, the derivative of this one, which is 5, and I put the 5 in front, okay? This one, the answer is itself, is an exponential function. But by the chain rule, times the derivative of tan, which is secant squared x. Now, which one you put first, it really doesn't make that much of a difference. It's probably better to keep it in this format. Now, the next one is very obvious, but I want to make sure we don't, make a mistake. So I'm going to rewrite this as e to the power of 2/3 times x, because in case you don't see it, this exponent means 2/3 x. So that's the same answer. If I want to differentiate, I get y prime is the same thing. But by the definition of the composite function, I need the derivative of 2/3 x. Gives me 2/3. I'll put it in front and I'm done. So very straightforward. I want to differentiate this rational function. Anytime you're dealing with a rational function or a fractional function, first you ask yourself, can I simplify it? The answer is yes. 2 is a prime number. 9 is 3 times 3 or 9 times 1. If you work it out, it ends up being this. In other words, if it's going to be simplified, you're hoping this goes away. So you can try it with x plus 3 to see if it works. Okay. Notice this is 2x squared. This is 9. What about the middle term? This is 6x. This is 3x. They add up to 9x. These two cancel each other. And that would be the final answer. So it's extremely important to use your algebraic techniques whenever you must. So y prime is equals to 2. There's really not much you have to do. Simplification of this rational function, putting it in lowest term, will do the job for us. We want to differentiate y equals 3 to the power of x, and we know the exponential functions, but what if the base is no longer e? Because everything we have dealt with, the base was e. So, for example, y equals b to the power of x. We are going to use logarithmic properties to make a change. I hope you remember ln of e to the power of x is x, e to the power of ln x is x. Therefore, we can change this to the following. According to this, I can say b is e to the power of ln b. So if I replace the b with e to the power of ln b, now I can use the power rule of exponentials. Remember, ln b is a number. So it's the product, e to the power of product of ln b and x. You just, okay, ln b and x. Now, again, ln b is a number. Imagine it was 5. So e to the power of 5x, the derivative is e to the power of 5x times 5. So what is the derivative? It's the same thing times ln b. ln b is a number, everybody. Now this one, look at this one. We bring it back to b to the power of x. What does it mean? If you have an exponential with a different base, the answer is itself. But because the base is not e, times ln b by logarithmic properties. Logarithmic properties. So I hope that's pretty straightforward. Therefore, if I want to differentiate, this is itself 3 to the power of x, because exponential. Is the base e? No. What do I need? ln of the base, ln 3. And you can leave it like that, because if you put that in front, one may read it as ln of 33 to the power of x. So the format that you write it, it makes a difference. What about y equals 2 to the power of 7x? Well, we use the composite function. So if it's b to the power of f of x, the answer is itself. The base is not e times ln b. The exponent is not x times f prime of x. This part is by the chain rule. Therefore, if I want the derivative of this piece, first, it's an exponential, the answer is itself. Second, is the base e? No. Times ln 2. Third, is this one x? No, it's a function of x. By the chain rule, I need the derivative of 7x, which is 7. And I rewrite it in this form. It's very straightforward, everybody. I hope you're okay with that. All right. Could somebody read this question, please?
Observations that show the length L in millimeters from nose to tail of a Siberian tiger can be estimated by the function L equals 0.25 W to the power of 2.6, where W is the weight of the tiger in kilograms. Furthermore, a young tiger's weight can be estimated in terms of its age, T, in days, by the function W equals 3 plus 0.21. A. How long is a tiger when it is 100 days old? B. At what rate is the length increasing when it is 100 days old?
Excellent. So part A is elementary algebra. You just plug in, you replace the T with 100, and that gives you the weight first. Of course, this is 21. With 3 gives you 24 kilograms, because the weight is in kilograms. But we want to see L. What is the length? Put 24 here. Replace the weight with 24. It does the job using a calculator, and we get 969.369 millimeters, almost 1 meter. I hope you remember 1,000 millimeters is 1 meter. So that's elementary algebra, and we're done. At what rate is the length increasing when it's 100 days old? Now we are looking at calculus. So I like to use Leibniz's notation. Leibniz's notation says dy dx is dy du du dx. That means y is a function of u is a function of x. So In this case, at what rate is the length increasing when it's 100 days old? That means with respect to time. That means we want dl dt. Now, to make sure we understand what we're doing, I want you to pay attention to this notation. Assuming there are two fractions, you can drop the du, it's dy dx. Do you see that? So we are going to put two fractions here, dl at top, dt at the bottom of the second one. Take a look. I want you to see how it's done. dl dt, I'm going to put dl at top of the first fraction, dt at the bottom of the second fraction. Now, L is a function of what variable? W. W is the intermediate variable. So dl dw, dw dt, if you look at this Leibniz's notation. What does it mean? Well, if you look at this one, it says take the derivative of this function with respect to w. In other words, in this case, w is your independent variable. So let's differentiate this one, everybody. So 0.25 times 2.6 times w to the power of 1.6. It's very straightforward. So this results in this. 0.25 remains. Exponent becomes the coefficient. And then w with the same exponent minus 1. 2.6 minus 1 gives you 1.6. That's dl dw. What about dw dt? That means look at this formula. Take the derivative with respect to t, simply 0.21. And we're done. Let's do the multiplication. This times this times this. Now, if they wanted the formula as a function of t, and you must replace this w with this. However, since they are asking for an answer in this case, just replace the w with, after 100 days, the width is what? 24. Make sure you know which number to use. You use 24 here. Put it into a calculator, gives you the answer, and the units, dl dt, units of the length over the units of time, 20.0532 millimeters per day, and whatever the number of decimals they asked you. This is the final answer. I want to show you also a slightly different method where composite function can be used, and in this case, it's not difficult. So first and foremost, L is a function of W. If I replace the W with this expression, 3 plus 0.21t, now we have L of t. So go to the function and find L of t, L of W, if you will, they're composite function. If I replace the t with 100, I get this answer. So if in this formula, I replace the t with 100, so this is the answer to part A, everybody. This is not part B, this is part A. What about part B? Well, we are going to rewrite L as a function of t. Which means L of t is 0.25 times W, 3 plus 0.21t to the power of 2.6. Now this is a function of time. We are going to differentiate. So 0.25 remains. 0.25 remains. 2.6, the exponent becomes the coefficient. You write the same thing to the power of 2.6 minus 1 or 1.6. And now the chain rule, the derivative of the inside, which is 0.21. I hope you see how we arrive at this. And if you multiply this number, and this number, you get this. This is L prime of t, or dl dt. And t is 100. And that gives you exactly the same answer as here. So two different approaches. One is that we use Leibniz's notation. One is that we find the composite function and do the job. However, I want you to know, sometimes finding the composite function, it may be more difficult. That's why you stick with the Leibniz's notation. You have to know both. Could somebody read this question, please?
The amount of glass recycled in a community is G of P equals the square root of 0.5 P squared plus 7 tons, where P is the population in thousands. It is estimated that T years from now, the population of the community will be P of T equals 4.4 plus 0.1 T squared, 1,000. How many tons of glass are expected to be recycled 4 years from now? And find the rate at which the amount of glass recycled is changed with respect to 4 years from now.
Excellent.
Include units in your answers.
Great. So again, the first part is very straightforward. We are looking at elementary algebra where t is given as 4 years. So if we calculate the population by replacing t with 4, 4 squared is 16. And times 0.1 is 1.6. With 4.4, we get 6,000. This is where the 1,000 comes from. 6,000 people. The amount of glass depends on the population. So replace the P with 6. And you get 36 here. 0.5 times that is 18. With 7 is 25. Squared of that is 5 tons of glass. This is where the units come from. All right, we're going to go with Leibniz's notation. dy dx is dy du dx. Because we want to find the rate at which the amount of glass, that means dg, is changing with respect to time, that means dt. So let me write dg dt. And then according to this formula, I'm going to put dg here and I'm going to put dt here. And I'm not going to put anything in between. We're going to figure it out. The in between is the other variable. G is a function of what? P, and P is a function of what? T. So G is a function of P, so we need dP here and dP here. What does it mean? It means take the derivative of G with respect to P. Whatever the answer is, take the derivative of P with respect to T and then multiply. So starting with that, I want to differentiate that. And to do so, I'm going to change that to 0.5 P squared plus 7 to the power of 1/2 so I can differentiate this using the extended power rule. So dg dp, everybody. This part. 1/2 sits in front times the same thing to the power of 1/2 minus 1 meaning negative 1/2. By the chain rule, the derivative of the inside, 0.5 times 2 is 1 times p. So this whole thing, 1/2, the same thing to the power of negative 1/2. The derivative of the inside is 0.5 times 2p, which makes it p. That's dg dp. Now we're going to go to the second part. Meaning we're going to work on this and differentiate it and put next to it that dp dt. So this is done. This is 0.1 times 2, 0.2t, 0.2t. This whole thing is simply 0.2t. And we know that p is 6 from the previous part, and t equals 4 here or here, doesn't matter. If you don't know that, you have to calculate it, okay? But we do know that from the previous part, so we're going to plug in. Again, if they wanted you to find this as a function of t, this p and this p, both this p must be changed with that, and this p must be changed with that, and then multiplied by 0.2, it becomes a function of t, everybody. But since they want just a number, we can do it by plugging in. So replace the p and replace the t. So let's see what happens. This is 1/2 remains. This one, everybody, is 36 times 0.5, half of 36, 18 with 7. So what we are looking at here is 25 to the power of negative 1/2, or 1 over square root of 25, or 1/5. This is elementary algebra. So this is 1/2. This whole thing is 1/5. Number 6 remains. These two give us 0.8. So again, 1/2. Everything here changes to 1/5. Number 6 remains. 0.14. The product is 0.8, and it becomes 0.48 tons of glass per year. dg dt, units of the numerator over the units of the denominator. So 0.48 tons of glass per year. The other method is to find g as a function of t, meaning replace the p here with this class. You can work on this. This probably takes more time to differentiate and get the answer. Can it be done? Absolutely. This is the composite function, but that's exactly why we learn both methods. Sometimes one is faster than the other. Okay. Differentiate cosine to the power of 10 sine x cubed. I'm going to show you how to do this. If you pay attention, it makes it very nice and easy. First and foremost, understand this is cosine to the power of 10. I highly recommend you rewrite it in this fashion. So you notice you're dealing with something to the power of 10, which means we are using the extended power rule. So that means that 10, the same thing to the power of 9. So 10 sits in front. Whatever this is to the power of 9. Now, the way you write it, you can write cosine to the power of 9 of sine x cubed. If you're more comfortable, write cosine of this thing. You could write this as cosine of sine x cubed. This is the argument, okay? When you don't have the power of 9 class, it's important to understand sine x cubed is the argument of cosine. So 10 times this to the power of 9. So 10 times this to the power of 9. Now we want g prime of x. That means we want the derivative of the inside. Now, the derivative of the inside. So cosine gives you negative sign. Negative sign of what? The same thing. Negative sign of the same thing. Is this x? No. Then we need to differentiate this now. Times the derivative of sine x cubed. What is the derivative of sine? Cosine. Cosine of what? The same thing. Cosine of x cubed. Is this x? No, it's x cubed, so times 3x squared. I hope you understood that. I'm going to quickly go over that again. I want to make sure that we are comfortable with that. First, you rewrite it in this fashion. Then you can even write g of x to the power of 10. So it's 10 g of x to the power of 9. So I need g prime of x. This whole thing is the derivative of the inside. This whole thing is the derivative of the inside. How do you take the derivative of the inside? Cosine gives you negative sign of the same thing. Sine gives you cosine of x cubed, and x cubed gives you 3x squared. We're just going to write this as 3x squared times 10 with the negative sign gives you negative 30x squared. Now, cosine of x cubed we write first, and then cosine to the power of 9 of sine x cubed, sine of sine x cubed. However you want to write that, but this is the final answer. This is a type of question you got to pay attention to because we can easily make a mistake. F of x is x to the power of 4, e to the power of 2x. The first thing I do, I put a raised dot in between. So I'm going to call this the f function. And I'm going to call this the g function. So it's f prime g plus g prime f. I'm looking at the product. So f prime is x to the power of 4 becomes 4x cubed times e to the power of 2x, 4x cubed times e to the power of 2x, plus e to the power of 2x is the g function, becomes itself because it's an exponential function. Is this x? No, then times 2. And then g prime times f, which is x to the power of 4. Notice 4 and 2, 2 is in common, x cubed and x to the power of 4, x cubed is in the common, e to the power of 2x is in the common. So first, your common factor is 2x cubed e to the power of 2x. Now, if you divide this one by this one, everything goes away, you get 2. This will give you 2. This one goes away, this one goes away, x to the power of 4 and x cubed gives you x, 2 plus x. So it's a simple factoring. I want to make sure that you get that. F of x is 9x times x minus 1 to the power of 4. Again, I want to put a raised dot here, everybody in between, and use, let's say this is f, this is j. You can even call this y if it helps. So we are going to go with the product rule. 9x, so we want f prime, which is 9, times g, which is x minus 1 to the power of 4, plus we want g prime, so I want the derivative of this piece, 4 times x minus 1 cubed, and then the derivative of the inside times 1. It happened to have a derivative of 1, the parentheses x minus 1, and times 9x. Now, in other words, g prime f. Now, f. Just to make sure we are okay with this, let me write that this is f prime g. This is g prime f. Okay. This was f prime g. This was g prime f. And so we're done. With calculus, we're done here. We are going to factor. What is in common? 9 is in common. What is in common? X minus 1. This has exponent 4. We go with exponent 3. So what do we need for the first one? Over here, when we compare, we just need x minus 1 to the power of 1 because this is larger by a factor of 1, right? So x minus 1. This one, 4, I don't see it here, so I'm going to put it. X minus 1 cubed, I have it. 9, I have it, and x is missing. Therefore, I'm going to put 4x. I'm going to put 4x. Now, all I have to do is just simplify the brackets. X and 4x, they add up to 5x. So the final answer is 9 times x minus 1 cubed times 5x minus 1. This is the final answer, everybody. As you can see, one step of calculus, not many, and many steps of algebra. Sine square root of 8x, if you have to write it in this fashion, again, it's up to you. Notice is sine of 8x to the second power. So in essence, we are using the extended power rule. We need the exponent 2 sitting in front becomes a coefficient times sine 8x to the power of 1. So 2 sine 8x to the power of 1. And then the g prime of x, now the derivative of sine 8x. Sine, the derivative is cosine. Of course, the same thing, cosine of 8x. And then 8x, we need 8. So one more time. 2 sits in front, sine of 8x to the power of 1. And then the derivative of sine 8x is cosine 8x times 8. Now 8 and 2, we get 16 sine 8x, cosine 8x. F of x is 3x times 3 to the power of x. It's obviously using the product rule. We are looking at the derivative of fg prime is f prime g plus g prime f. Again, if you want, if it makes it easier, assume this is f, this is g, and this is y equals that. So we want f prime. The derivative of 3x is 3 times the second one, 3 to the power of x. And then the derivative of 3 to the power of x, any exponential, the answer is itself. Is the base e? No, times ln 3 by the logarithmic properties. And now times f 3x plus, this is the f part. Let me just write at top of it so you be clear. We have f prime g, g prime f, okay? And we are done. Let me put an asterisk next. We are done with calculus. We are going to use our algebraic techniques to finish the job. First and foremost, notice 3 has exponent 1, therefore it's 3 to the power of x plus 1. This one has the exponent x, this 3 has exponent 1. So this 2, everybody, also become 3 to the power of x plus 1. And the rest, ln 3 and x, remain. Therefore, this is in common. And what remains from the first one is 1, and from the second one is x ln 3, and we are done. So this is the way you factor. I want to make sure that you understood the factoring. This is in common, so 1 plus whatever is left. ln 3 times x, normally we write it as x ln 3 because I don't want anybody to be under the assumption is this is ln of 3x. All right. Implicit differentiation. Functions expressed by one variable are defined explicitly in terms of another variable. Example, y equals x squared minus 2x plus 1, or in general, y equals f of x. However, some functions are defined implicitly by a relation between x and y, such as x squared plus y squared is 25, or x cubed plus y cubed is 6xy. And in some cases, it is possible to solve such an equation for y, and in some cases, it is not easy to do so. In some cases, it's just impossible. So what I want to do as a warm-up example, I want to look at this, and I'm going to do it both ways. Explicitly, I'm implicitly showing you that they both result in the same thing. Explicitly, because we can easily solve for y. So in this case, if I move the 4x to the other side and divide by 2, I get y equals minus 2x plus 5. So move and divide by 2. Clearly, y prime is negative 2. Explicitly. How about implicitly? Well, given the original function, original relation, if you will, 4x, we know the derivative is 4. What about 2y? 2y prime or dy dx. By the way, y prime is the same as dy dx. Y is a function of x, and you can imagine y is the same as g of x, everybody, okay? So if it makes it easier, write 2 times g of x. The derivative of that is 2 times g prime of x, okay? So 2 times dy dx or y prime, and any number gives you 0. On purpose, I put dy dx because I want to tell you that they are the same. So I move the 4 and divide by 2, and we get the same answer as before, meaning either way is fine. Makes no difference which method you take. As long as you're consistent, you come up with the correct answer. However, as I mentioned, in some cases, it's impossible to solve for y. Here's an example that we want to do implicit differentiation. We want to find dy dx. And what I want to remind you, by the way, when we have a g of x to the power of n is n g of x to the power of n minus 1 g prime, if we have y to the power of n, compare these two, becomes the same thing. N instead of g of x, y to the power of n minus 1 y prime. That is extremely important. So let's differentiate this. An expression is in the parentheses to the power of 4. So we have a 4, the same thing to the power of 3. And by the chain rule, the derivative of the inside times 2 plus y prime or dy dx. That's the left side. Let me remind you of this extended power rule one more time. 4 sits in front, becomes a coefficient. Whatever it is, you write it to the power of 4 minus 1. Now, the chain rule says we need g prime of x. The derivative of the inside is 2 plus either y prime or dy dx. Sometimes it's easier to use y prime, but I interchange them because they both mean the same thing. Now the right side equals 1 minus 2y becomes 2y prime. 1 minus 2y prime. Believe it or not, this is the end of the story for calculus. The rest is elementary algebra. Solve for y prime. Solve for y prime. Let me go through the process. There are a few steps. Those are all algebraic. So first I'm going to multiply this one by 2, and I get 2 times 4, 8, times this mess. And then I'm going to multiply 4 by this by y prime. Okay, so 2 times 4, 8 times this mess. And now this one times 4 times y prime. Why am I putting it in this format? Because remember, we want to solve for y prime. We want to bring everything involving y prime to the same side. Therefore, here's how I'm going to move things. I'm going to move this to the left, becomes positive 2y prime. And I'm going to move this to the right, becomes minus negative. Okay. On the left side, I want to factor out the y prime. I want to factor out the y prime. So from the first part, everything in blue remains. From the second part, number 2. The right side, I don't have to do anything. So what is y prime? If you can simplify it, you can do that, but this can't be simplified. So basically, y prime is the right side divided by the brackets. You call it y prime or dy dx. By the way, again, dy dx is telling you that x is the independent variable. Use implicit differentiation to find dy dx. So sine, never mind this, sine gives you cosine. Cosine of what? The same thing, y. So cosine y, dy dx or y prime. Please understand, this, you can think of it as g of x, okay? Sine gives you cosine y, and then y gives you dy dx. To do this, it is extremely important to realize it's a product rule. So if I put a raised dot here and think of this as f, think of this as g, we get plus f prime, which is 6x squared times g or y squared, plus g prime, which is 2y, y prime or 2y, dy dx times f or 2x cubed. Please understand this part. So let me write it in this fashion. So this is f prime, this is g, this is g prime, this is f. So I want to make sure everybody's comfortable with that. The derivative of y squared is 2y dy dx. Change it to g of x practically. So 2 times g of x and g prime of x times the first part. So this is the only calculus step, and we are done. We are solving for dy dx. So first, let's put these two together. Put these two together as 4x cubed y. So I didn't change much. Just this one, I put it in front. Since we want to solve for dy dx, we are going to move this, and this one we take dy dx as a common factor out. And all you have to do, divide both sides by the parentheses, namely cosine y plus 4x cubed y. And that's the final answer. We are dividing by this expression. We want to find the equation of a tangent line for this function x e to the power of y plus y e to the power of x equals 1 at 0, 1. Which means we need two things, a pair x comma y, which is given. We also need the slope, which means we have to differentiate, and we are going to differentiate implicitly. So for the first part, if I put a raised dot here, and I assume this is f, this is g, I have f prime, which is 1, times g, which is e to the power of y, right? Plus the derivative of e to the power of y, it's exponential itself, times the derivative of y, which is y prime or dy dx, and then times x by the product rule. And I'm going to write at top of it this would be f prime g, this would be g prime f. We do the same thing here. Again, if I call this f and g, the derivative of y is y prime or dy dx times e to the power of x plus the derivative of e to the power of x is itself times e to the power of x times y. According to that, again, for this one, we have f prime g plus g prime f. Okay, what is it that we want to solve? You can plug in, you can replace the x with 0, y with 1, and the result will be giving you y prime. And that's what you want as a slope. But I want you to solve for y prime. This is really a better strategy. How do we solve for y prime? Anything involving y prime, we keep. Anything that doesn't have it, we move. So this goes to the other side, becomes negative. This goes to the other side, becomes negative. And for this part, if you factor the y prime, because that's all we want to solve for, this one would be e to the power of y times x, and this one would be e to the power of x. So if you divide both sides by this part, the parentheses, we get y prime or dy dx. Now, what is the slope? Plug in. Replace the x with 0, the y with 1. So minus e to the power of y, that means e to the power of 1, plus e to the power of x, which is 0, that makes it 1, and y is 1, so it's 1 times 1 over 1. The bottom, e to the power of y, that means e to the power of 1 times x, which is 0, and then plus e to the power of x, which is e to the power of 0, making it 1. This is the exact answer. So do I have to go with y minus y1 equals m times x minus x of 1? No, I'm going to go with y equals mx plus b, because this is the y-intercept. And when I do that, okay, so by the way, this is the simplified version. I get y equals mx plus b. And that's the final answer. And that's the precise answer, everybody. That's the precise answer, keeping it at E.